This presentation will take you through the process of preparation and construction of a concrete canoe that will be competing in the Pacific Southwestern Conference, held in Tucson, Arizona. It will be hosted by the American Society of Civil Engineers in April of 2015.
Hello, my name is Angelica Rojas, and I was in charge of the project management for the concrete canoe team.
Hello, my name is Jacqueline Villa, and I was in charge of hull design.
Hi, my name is Jason Labradette, and I'm in charge for the mix design of the concrete canoe.
I'm Benjamin Toth, and I was responsible for structural analysis.
Hi, I'm Joseph Lopez, and was in charge of construction.
Our objectives and goals for this project include designing a hull that maximizes speed and stability, creating a mix design that is strong as well as lightweight. We have also taken on the challenge of designing the thinnest concrete canoe in San Diego State history, with a sidewall thickness of 0.2 inches. We are determined to crush our competition in the Pacific Southwest and compete in nationals. And now I would like to introduce Angelica, who will discuss the aspects of project management.
As a project manager, I was in charge of creating a schedule and setting strict deadlines. I monitored and oversaw each division to make sure everyone remained on track. I also organized weekly meetings where each member of the team gave an update of their progress and where we addressed how to overcome any conflicts that we encountered. Another of my tasks was to contact companies and coordinate meetings with professional advisors who offered the team their guidance and support. I also contacted suppliers for sponsorship and discounts, which allowed us to reduce the cost of the project significantly. Another thing I was in charge of was ensuring access to labs and machines so that the team was able to perform necessary analysis that aided in the final design of a canoe that will perform exceptional in the competition. Furthermore, I planned for pour day so that the team, along with volunteers, had everything that was needed available to be able to successfully construct the canoe. All these tasks were crucial in order for the concrete canoe to be constructed by the set deadline.
Thank you, Angelica. That was quite rewarding. Now here's Jacqueline with our process of hull design.
A lot of research was done to determine the most optimal hull design for a concrete canoe. As a team, we focused on basic characteristics necessary for La Sirena to perform well during the race portion of the competition. The races require canoes to travel at high velocities in a straight path and be maneuverable. In watching the performance of canoes in past competitions, there were many areas that needed improvement. Some canoes had a high rocker, which prevented an intended sharp entry line to break through the water surface and created difficulty in steering. For our analysis, we use a hydraulic channel to determine how various hull designs affect the flow. We 3D printed scaled models varying in lengths and widths, and a model consisting of a keel. Last year's hull was used as control. This analysis would give insight on the turbulent or laminar properties each hull would offer. For example, the wider model performed with low turbulence and created more of a laminar flow, whereas the more narrow model created more turbulence. From this observation, a wider model would be best. La Sirena is a foot shorter than El Luchador at 20 feet. A shorter hull will help with turns, and a keel was added to create a more streamlined flow and allow the paddlers to focus more on speed than in steering. The shallow V profile will aid in maneuverability and resist tipping. The widest point of the canoe of 30 inches is located a foot from the center to create a sharp entry line, and with a moderate rocker, create a lower bow height, improving the issue past canoes had of having a too high of a rocker.
And now Chasen, our expert in mix design.
The goal this year was not to redefine last year's concrete mix design, but refine all research, testing, and techniques of previous years. Cementitious materials used were Type 2/5 Portland cement, Class F fly ash, and silica fume. We chose to add more Class F fly ash than cement in order to increase compression strength and decrease permeability. Fibers used were PVA glass fibers, intended to increase tensile strength and reduce cracking. Aggregates used were expanded glass beads ranging from 0.03 millimeters to 2 millimeters, and K20 glass microspheres used as a fine aggregate. Liquid admixtures included Riotech Z60 for a workability retainer, Acryl 60 for bonding and modifying admixture, Mastercast 750 as a plasticizing admixture, Styrofoam latex as a water reducer and polymer modifying admixture, Derex 2 for air entraining, and Masterset Belvo for hydration control admixture. The following video is an example of our mix procedures. Here we go. Our final mix had a density of 56 pounds per cubic feet and a 28-day compressive strength of 1020 psi and a 21-day tensile strength of 92 psi with an air content of 10%. Over 15 trial mixes were made in order to adjust batch weights and ratios to the optimal amount.
Next is my analysis of structural design. The preliminary structural analysis of the concrete canoe was done in 2 dimensions, considering 3 separate load cases. The first and second load cases involved 2, then 4 paddlers sitting in the canoe whilst it's resting in water. By assuming that the concrete is a uniform beam and fixed at both ends, along with introducing the self-weight of the concrete and the weight of the paddlers, it is simply a matter of solving for equilibrium to obtain the buoyancy force pushing against the canoe. Once all of the forces are known, by utilizing singularity functions, a moment equation can be written to solve for the maximum moment in the canoe, as well as its location. Using this maximum moment, the flexure formula is then used to develop the maximum tensile stress acting in the canoe at the location of maximum moment, which calculates to be 58 psi. The bottom of the canoe experiences the brunt of this tensile force. A safety factor of 1.5 is used to account for unforeseen conditions and unexpected loads. This makes the ultimate tensile stress requirement 87 psi. Since the tensile capacity of the concrete was found to be 70 psi, a reinforcement option was found to be necessary. To get a better simulation of what stresses actually will form in the canoe, a 3-dimensional analysis was implemented. Finite element analysis was used on a 3D model of La Serena. Water was represented as springs at all nodes on the underside of the canoe. Also, the mass density of the concrete and the weight of the paddlers were entered into the computer program SAP 2000 to complete the load case. The results were quite similar to that of the hand calculations, with a maximum tensile stress of 85 psi located under where the paddlers sit. The reinforcement options used were a carbon fiber mesh and a 23-gauge quarter-inch welded wire mesh. The carbon fiber is the strongest of the reinforcements implemented, with 290,000 psi of tensile strength. Since the carbon fiber is much too stiff to make the curve from the bottom of the canoe to the side, the welded wire mesh was used to reinforce the areas where the carbon fiber couldn't. The carbon fiber and welded wire mesh were placed in between 2 0.1-inch concrete layers. Checking the depth of the concrete was an integral part of keeping a uniform thickness of 0.2 inches. Last, but certainly not least, Joe will explain the construction process.
Lasadiana required delicate procedures for her final appearance to be memorable. We started with specifically designed files from our hull designer, which were converted to readable files for the water jet to cut. Once the 4 3/4 inch thick styrofoam sections were cut, assembly was next. We spot sprayed foam the sections together and kept alignment with a true 20-foot 2x4. Next, we planed, sanded, and finish sanded the mold. Once the mold was complete, we covered it with one 8-ounce fiberglass layer. Overnight curing allowed us to cut the mold into 5 pieces for delivery and demolding. We decided to use carbon fiber mesh for the bottom and sides of the canoe. The radius was covered with 1/4 inch 23 gauge welded wire mesh. Pour day commenced with the help of 20 volunteers. We started by making the first layer 0.1 inch, installed reinforcement, then a second layer of 0.1 inch, molding a keel, then finished troweling. Irrigation hoops and plastic vapor barrier were installed to achieve maximum strength. Our curing table was a 3-rail system with misters. The curing process involved a 20 psi regulator and 40 360-degree misters that overlapped with each other 6 inches for a spraying capability of 22.5 feet. A timer was set on the hose bib and set to spray 4 times a day for 3 minutes each. The canoe was demolded 9 days later. Finished patching, light sanding achieved a finished canoe. Our challenges this year were to build a monolithic 0.2 inch thick canoe that was seaworthy.
In conclusion, it has been my pleasure to narrate and introduce the people responsible for designing and constructing a full-scale working model of our concrete canoe, La Sirena. We have covered the 3 fundamental processes of any civil engineering project: conception, design, and construction. We have utilized several major disciplines in civil engineering, being project management, fluid analysis, material engineering, structural analysis, and construction engineering. Thank you for your interest in our project, and hope you have learned a little of what it takes to produce a canoe made of concrete. Cheerio.